now we're going to start applying the principles of circular motion to gravity. Now, as the story goes, Newton was sitting under an apple tree, and an apple fell off and hit him on the head, and all of a sudden he realized that gravity was not only pulling this apple off the tree toward the earth and caused it to hit him in the head, but it also could very well be the force that was causing all of the planetary motion in the universe. Now, whether that story is actually true, we're not entirely sure that the apple actually hit him on the head. There is a good part of truth to the case that when he saw the apple fall, that's what made him think, maybe gravity has a bigger effect than what we realized that it actually had. And so he actually did a lot of work in this area, and the work that he did helped to prove some of Kepler's laws of planetary motion. And so we're not going to get into all of that, but it did tell him that the gravity that we are experiencing is also the same thing that is causing a lot of the planetary motion. So let me explain it to you this way. Let's say that you have, this is going to be a really bad picture, I'm going to warn you ahead of time. Let's say, I need it to go on the other end. Let's say that you have a cannon, and your cannon is shooting a cannonball. Now, we all know that when you shoot a cannonball, the ball comes out and it will land on the ground, right? Okay. So let's say then that you have a cannon and it shoots with more force. And so let's say that if this shoots this cannonball with more force, it actually comes out and the ball goes a lot further before it lands on the ground. Let's now assume that I have a cannon that is so strong, has so much force behind it, that when I shoot the cannonball, it falls to the earth, but it falls at the same rate that the earth curves. Now, there actually isn't a cannon that can shoot with that much force, but what we have actually done in order to put a satellite into orbit is this same type of thing. If you use rockets and shoot the satellite into space with enough force, it is actually in free fall and it is falling back towards the earth, but it's falling at the same rate that the earth curves. And so therefore, when that happens, that satellite is actually in orbit. And so, yeah, satellites are falling, but they're falling at the same rate that the earth curves. And so therefore, they stay the same distance from the earth all of the time. So that happens with satellites artificially. It happens with planets as they're orbiting suns, as with moons as they're orbiting planets. They're actually in free fall, but they're falling at the same rate that the thing that they're orbiting is actually curving. Now, there are some 3 principles of the law of universal gravitation. And once again, I've written those principles out for you on the sheet with all the video problems on it. So I don't have them written on the board today because I'm going to need my board to work some other example problems for you. But the first one, excuse me, says that all objects with mass are attracted to one another by a gravitational force. Now, we normally think of gravity as being something that only very, very large objects have, suns, planets, moons, and things like that. But in reality, everything has a gravitational force to it. It can be really, really tiny. So if you remember Newton's third law of motion, or Newton's third law, it basically says that there's an equal and opposite force anytime a force is exerted. And so the earth is exerting a force on us, but we are exerting a force on the earth at the same time. Now, the thing is, the earth is so much more massive than we are that it exerts a much larger force. And so the force that we exert on the earth is so tiny that it's almost not even noticeable. When the objects are closer to the same size, the force that they exert on each other is much more noticeable. And so the other 2 principles of universal gravitation help us determine exactly how much those factors are going to affect the gravitational force. Now, your book actually gives you a formula for gravitational force. We're not actually going to be using that to solve any problems, and the reason is just mainly because one of the constants that they put in there is an absolutely teeny tiny number, and something like that for the level of math that most of you are at, those calculations are going to be difficult because that number is so tiny. It's a 0.00000, and there's like 10 zeros before you ever get to the first number. And so the number is really tiny. So we're going to go at this more from a conceptual viewpoint in place of actually doing a lot of calculating of actual forces in newtons. Okay, so the second part of the law of universal gravitation says the gravitational force between two masses is directly proportional to the mass of each object. Now, that's really what I kind of said just a second ago. The bigger the object, the more gravitational pull it has. So, if your masses, and if you have to have two masses interacting on each other. So, if your masses, product of your masses is going to go up, what that means is your force is going to go up as well. The third part of the law of universal gravitation says that the gravitational force between two masses is inversely proportional to the square of the distance between those objects. So basically what that's saying is that the further away the two objects get, the less gravitational attraction exists between the two of them. And again, if you think about that, that makes sense. I mean, Pluto is so far away from us that Earth's gravity doesn't have much of an effect on Pluto. So the further away that you get, the less the force it actually acts on it. And in this case, it's actually the square of the radius between the two objects. So if the square of the radius goes up, the force is going to go down. So let's work through a few sample problems so you can see what we're talking about here. All right, the gravitational force between two objects, mass 5 kilograms and 2 kilograms, is measured when the objects are 5 centimeters apart. The distance between them is increased to 10 centimeters. How does the new gravitational attraction compare to the first one that was measured? Well, the best way to work these problems is by drawing a picture. So what we're going to do is I'm going to draw my first two objects, and I have a 5 kilogram mass and I have a 2 kilogram mass, and it says that there is 5 centimeters between them, okay? Then it says that we're going to keep the same two masses, but the distance between them is going to be increased to 10 centimeters. So here's my 2 kilogram mass over here. And now they are 10 centimeters apart, okay? Now, as I do this, I am going to try to color code this so that it makes it a little bit more easy for you to understand this. So since we're talking about the distance between them, notice the masses have not changed. So in this case, this particular part of the universal law of gravitation isn't going to be affected at all. Okay, so here my distance has gone from 5 to 10, so that means that this has gone up by a factor of 2. So for distance, what matters is the square of the distance. So for distance, what I see is that the distance has gone up by a factor of 2, but I have to square that. And so remember, when we square things, that just means multiplying them by each other. So 2 times 2 gives me 4. And so what that means is that the force is 4 times less than it was before, okay? 4 times smaller. Or you could say that the force is 1/4 of what it was before. You could actually flip it upside down and say it that way, okay? So let's now look at a problem where we're going to change the masses on it. So we'll make some more space here. Okay, so the second problem says that the gravitational force between two objects, this time I have a mass of 10 kilograms, and I have a mass of 6 kilograms. And the distance between those two objects is 10 centimeters. Okay, then the problem says the 10 kilogram mass is replaced with a 20 kilogram mass. So I'm going to replace that one. And it says the 6 kilogram mass is replaced with a 3 kilogram mass. But I'm not changing the distance between them. I'm going to leave them 10 centimeters apart. All right, so what is that going to do to the attraction between these two objects now? Okay, so if I go from, since this stays the same, I'm now only looking at masses. So if I go from 10 to 20, this has gone up by a factor of 2 because 10 times 2 will give me 20. If I go from 6 to 3, how did I get there? Well, to do that, I had to divide by 2 in order to get from 6 to 3. So now that I have a change in mass, I multiplied by 2, but then I also divided by 2 over here. Well, 2 divided by 2 equals 1. And so what that tells me is that since I doubled this one, but I halved this one means that now my force is actually not even going to be changed because I changed this one by the opposite factor that I changed that one by. Okay? So now let's do a problem where they're both changing and let's see what happens with that. So once again, we'll get rid of this and we'll make some more space. Alrighty, so the gravitational force between two objects, this time I have a 1 kilogram and a 2 kilogram mass. So this one is 1 kilogram and this one is 2 kilograms. And it tells me that the distance between them is 10 centimeters. Like that. And then it says the objects are going to be replaced with 2 different masses. So this mass here is going to 4 kilograms, and the second mass is going to become 1 kilogram. Oh, whoops. And we're going to decrease the distance between them to 5 centimeters. So I'm actually going to put these a little closer together than I had it. So this was 1 kilogram. And now there is only 5 centimeters between them. So now, how does the gravitational force change between what it was before? So let's look at the mass first. So from 1 kilogram to 4 kilograms, what did I do in order to get from 1 to 4? Well, I had to multiply that by 4. Okay, what did I have to do here? Well, to go from 2 kilograms to 1 kilogram, I had to divide by 2. 2 divided by 2 is 1. So for the mass, I took 4 times greater, and then I divided it by 2, which gives me 2. So as far as just the mass is concerned, my force is now 2 times bigger than it was before. Okay, now let's look at what effect the distance is going to have. To get from 10 centimeters to 5 centimeters, I had to divide that by 2. So when I think about distance, remember that we always have to square the distance. So I took 2 and I squared it, which is going to give me 4. But for distance, the further away they, or the closer they get together, the stronger that the force is going to be. So since I pulled those together, the force is now going to be stronger. So because of the distance being less, the force is now 4 times bigger than it was before. So when you're determining the distance, the effect of the distance on the force, you have to pay attention to whether you're going further apart or whether you're getting closer. If you're getting closer, then the force is going to get stronger. If you're getting further away, then the force is going to get smaller. All right? So The effect of the mass was that the force was 2 times bigger. The effect of the distance was that the force became 4 times bigger. And so then overall, 2 times 4 times is going to give me overall an effect on the force is going to be 8 times bigger than it was before. Okay? I gave you quite a number of problems to work today so that you will have some practice working on that. And so if you have any questions, make sure that you contact me so I can help you.